talk about math. More specifically, linear regression. Have I had too much coffee today? Yes. So let's say you've got a set of data, say housing prices. Now, you can use linear regression to find a line that fits your data. You can use this line to find trends and to estimate where the next plot point will be. So if you're given an x-coordinate, you can estimate the corresponding y-coordinate. This is fantastic for modeling complicated systems. If you can find a linear model to model a system, you have struck gold. You are a fortune teller. You have simplified a complex system into a one-dimensional line. And you can use this line to predict things about your system. But Rin, this sounds complicated. Never fear. Math is here to simplify the matter. So, given n data points, x1, y1 through xn, yn, we're looking for the estimated values of beta naught and beta 1, where the estimated y value is beta naught plus beta 1x. On this lovely 2D graph, we've got two data points, x1, y1, and x2, y2, giving us this estimate line. This line is made from x1, y1 hat and x2, y2 hat. We use the deviation between y and y hat to determine how well our line fits the given data. So y isn't always continuous in general. yi allows us to refer to the value of y corresponding to a given xi. E sub I is the aforementioned deviation between y and y hat, the difference between the actual data point and the estimated prediction. As we change beta naught, we'll shift the line up and down along the y-axis. Changing beta 1 will shift the slope. The sum of squares error, or SSE, is a function of beta naught and beta 1, which is the sum over I of e sub I squared, which is the sum over I of the deviation in y value squared. Now that you know that, I can reveal to you the basic principle of linear regression. We're going to choose beta naught and beta 1 such that we minimize the sum of squares error. In order to minimize the sum of squares error, we must solve the following system: the minimum SSE with respect to beta naught and the minimum SSE with respect to beta 1. The solution of this is called the least squares estimate. We solve this system by finding beta naught and beta 1 that satisfy the system, where x bar and y bar refer to the average values of x and y respectively. The sum of squares total, or SST, Sierra Sierra Tango, is a summation over I of the difference between any given y value and y bar squared. Recall that the sum of squares estimate is the summation over I of the difference between any given y value and y hat squared. R squared is 1 minus SSE over SST, where R squared is the coefficient of determination. The value of R squared is limited to the closed interval 0 to 1, where 0 is the worst case fitting the data poorly and 1 is the best case fitting the data well. Allow me to illustrate with an example. So we can set up a table. Given x and y, we can fill these two columns. The average values of x and y are our x bar and our y bar. Now that we have the values of x bar and y bar, we can solve for the difference between xi and x bar for each data point, and the same for yi and y bar. We find that the summation of the values found by multiplying these two columns row by row is 140,000. We find that the summation of the values found by squaring the difference between x and x bar row by row is 32. Now that we know the values of these two summations, we can calculate the least squares estimate of beta 1, and thus, that should be a plus, the estimate for beta naught. We find that our y hat is 7,000 plus 4,000x. Now we want the sum of squares total. We find that the summation of the values found by squaring the difference between y and y bar row by row is 994,000 squared. Don't worry, the kilo squared cancels later. Now we want the sum of squares error, so we use our y hat to calculate the yi hat for each xi. Then we find the difference between yi and y hat, square it, and then take its summation over I to get 15 kilos squared. Now that we have the SSE and the SST, we find that our coefficient of determination is sexily close to 1. But wait, if we use a different y hat, say y hat is equal to 4,000 plus 6,000x instead of 7,000x, will we find a coefficient of determination closer to 1? Let's see.
The sum of squares total does not depend on y hat, so it will not change. We have to recalculate the sum of squares error. Again, we're going to find the difference between yi and y hat, square it, and then take the summation over I, resulting in 98 kilos squared. Using the new SSE, let's recalculate the coefficient of determination. We find, nope, it's not closer to 1. As we know, r squared resides in a closed interval, and we've used r squared to prove that our original y hat fits the data better than this y hat.
And you can use this line to Math is awesome. Math, 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 math.